Hello, everyone. My name is Molly Halsey, and I am the event specialist here at EDB. I will be your host today for our webinar, Reference Architectures. I'm joined by Dave Page, VP and Chief Architect of Database Infrastructure, and Vibhor Kumar, Chief Performance Architect. And before we get started today, I just want to go through a few housekeeping items. This presentation is being recorded. We will be sharing the recording along with the slides after the broadcast. The lines are currently muted. If you have a question, please feel free to submit it in the question panel. Today's session is scheduled for 1 hour. We expect the presentation to last most of our time, and we will allot any extra time for Q&A. If we do not have time to address all questions, we will follow up afterwards with any attendee whose question was not answered. Now, without further ado, I give it over to Vibhor and Dave.
Good morning, good afternoon, good evening, everyone. Welcome to today's webinar. So on the agenda today, we'll have a quick introduction to EDB. We'll look at what the reference architectures are. And then before we dive into them, we'll just look at a few of the properties so we can understand what we're talking about as we describe the different architectures. We'll then go through the core database server architectures that we've prepared at the moment, as well as what we're referring to as add-on architectures. And then there'll be a quick summary at the end and some Q&A. So, who is EDB? I imagine if you've worked with Postgres, you're more than likely familiar with who we are. We're the largest dedicated Postgres company in the world at the moment. We recently acquired Second Quadrant and added them to the team, which gives us over 25 committers and recognized contributors to Postgres. We have somewhere around 5,000 lifetime customers, including over 25% of the Fortune 500 companies, and offices dotted, well, around the world, and headquartered in Bedford, Massachusetts, as well as offices in various locations in Europe and Asia, UK, Italy, Netherlands, Germany, Spain, India, Japan, for example. We have a combined product portfolio that supports enterprise PostgreSQL requirements, right from extreme high availability, scalability, and security to hybrid cloud and geographic distribution. If you've been to any of our webinars before, you may well recognize the graphic in the slide there. We've been recognized now by Gartner in their Magic Quadrant for databases for 7 years now, something that we're very proud of. So,
thank you, Dave. Thank you. So, yeah. So before we start, I think the key question always comes is, what is reference architecture, right? And why do we need it? So, reference architecture you can think as are the pre-designed, tried, and tested templates for the deployment patterns, and users can use it to deploy Postgres in their production environment, in the dev environment, or in their test environment. Other way to think about this, where the reference architecture can be defined as a different levels of abstractions for the deployment as a starting point. The main intent of the Postgres reference architecture is to give guidance on Postgres initial deployment based on the business continuity plan which customers and users have. It also will serve as a quick try the reference architectures, mainly like you can deploy as it is in your environment or in your production, and you can treat it as a foundation for deploying other tool sets on the reference architecture. Again, it purely depends on what are the important criteria or business need you want to cover using the reference architectures. Next slide, please. There are some key properties of the reference architectures. One of them is called recovery time objective. Again, the key properties are essentials because this way you can decide which reference architecture you would like to deploy in your environment, or the foundation which you're deploying, on which what are the important components or important capabilities you would like to add to meet your business continuity. The first is the recovery time objective. Recovery time objective, sometimes people call it as a estimate time of repair, is actually related to the availability. That is the total time required for planned outage or time needed to fully recover your system or environment from an unplanned outage. Reference architecture covers these components, and it also covers important components to meet the requirement of your recovery time objective. Next slide, please. The other key property of the reference architecture is called RPO. RPO is measured of time from the failure, disaster, or comparable loss causing events. It can be measured, or it can be used to measure some important items or key points, I would say. That is, for example, how far back you can go when disaster happened, right? What is the usable point or usable data which you can recover? It also determines how frequently you should back up your data. It also represents some additional need for the restore time, recovery time. I mean, you can think in another way. The recovery point objective actually allows you to measure how much data loss you can bear in case of disaster. Okay. For example, if you have an RPO for 2 hours, it means in case of a crash, you may forget everything that you did in the last 2 hours, and you still will be able to recover data 2 hours ago. So this is kind of an important item. For some, again, 2 hours is a very big time I'm giving you. People actually go with recovery point objective of 2 minutes, 3 minutes, or near zero data loss. Reference architecture can really help you to achieve the RPO of near zero data loss kind of a environment. Next slide, please. And the other important architecture property you can think about is called geographic redundancy objective, GRO. It's also very, very important, right? So you can think about this way: if you have many data centers and something happened to your one data center or data center in one country, right? How would you recover your data into the other data center or other region? So it's merely actually RPO, RTO for across geography you can think about. So as I covered the recovery time objective, recovery point objective, this is GRO actually covers recovery point objective, recovery time objective across the geography, which is making services available across geography. The next property is the called target availability. Again, a lot of people know about the high availability, how we measure the high availability. So target availability is again synonym of the high availability. It's a percentage of uptime in a given year based on your service level agreement with your customers or with your users, right? Generally, we measure the target availability or high availability in nines. For example, if you have a 4 nines of the high availability or target availability, it means you have you can bear 52.60 minutes per year of the downtime, which actually maps out to the 4 minutes 38 seconds per month, and which again maps out to the 1 minute 1 second or 0.1 second per week, right? We can see when you talk about the 4 nines, we define the time, how much downtime you can actually allow per year or per month basis or per week basis or per day basis. There is a more elaborate discussion around it, and I think Dave will be covering some more aspect about these nines in the presentation. But overall, target availability is a key point, because when we present the availability of your environment or of your system, we present in terms of nines. Dave?
So yeah, I think it's worthy having a note here on target availability. a target is not a guarantee. So when we say target availability, this is what we're aiming for in terms of availability and what we think is possible. The problem is basically that availability is affected by a lot more than just the database server. As you can see from the list on the slide there. We need to take into account the operating system, the hardware, the network, the environment, so whether we've got sufficient power, cooling, even, you know, if the cleaning staff, for example, has tripped over the power cord and brought the server down that way. We also need to allow for things like upgrades and maintenance. And as you can imagine, for a software vendor like EDB, we only really have control over the software that we provide. We have no control over the quality of your hardware, your operating system, and so on. So what we'll quote in the following slides are what we believe are the maximum target availabilities that, assuming there are no other problems or no environmental failures, power failures, that sort of things, that our software is able to achieve. So let's dive into some of the core architectures. So what we've done is we've split up our reference architectures into what we've called the core architectures and add-on architectures that I'll talk about some more later on. The core architectures are basically the database server itself. So this can comprise of one or more nodes that are running Postgres and can be configured in different ways. Now, the architectures that we're presenting today, we've started with Postgres' built-in binary replication, or streaming replication as it's known, as well as a single node, which obviously has no replication. And over coming weeks and months, we'll be extending these reference architectures to include other options as well, looking into different deployment patterns. So, for example, containerized deployments and potentially things like logical replication. But for now, we're just going to be talking today about the streaming replication, which is probably the most common that you'll find and one of the easiest to set up. So the first architecture,
single node architecture is the first one, which is very well known, and a lot of people use it. And again, some people actually use it into the production environment too. It's a very basic deployment where you actually have one node of the Postgres, and you have already defined your recovery time objective, recovery point objective. In this architecture, again, target availability which you can get is called 3 nines, right? And there is no geographic redundancy available or GRO available through this single node architecture, because you can think about having a one node in one data center. If something happened to that data center, you don't have the redundancy or any way to have this node available or replica of the node available across the region or across the geography. So geography or GRO is not covered in the single node, but people use it in the production for the non-critical applications. And they also use the single node architecture for their development and testing purpose. It is generally not recommended for the critical application because this architecture is specifically meant for the non-critical and testing and development environment. So here is the one diagram which you can see. You can have a single node architecture. There is one database server running in the one virtual machine or one machine, right? And you have different volumes attached to this server. And these volumes, I mean, you could have a data volume, you can have a separate vol volume. And in case if you're using indexes, you can have indexes too. Now, within this same data center or same region, right, you can actually achieve certain level of the RPO, RTO. Like as I mentioned, the RPO, you can have the RPO of near zero data loss using the this architecture too, because if you are keeping the separate volume and something happened to your machine or your virtual machine, you can spin up a new virtual machine and attach these volumes together, and you can still have the zero data loss. Recovery time objective is pretty much dependent on how you are actually building these virtual machines. In some environment or in some customer's environment, what people do, they create an image called golden image, and they actually spin up the new virtual image, virtual machine using that called golden image, and they attach these volumes. Again, recovery time objective actually is not really, as we mentioned in the previous slide, is not linearly, cannot be close to the 5 nines. It actually helps you to achieve at least 3 nines. That's why when you're using it, you could use it for your non-critical application, or you can use it in your test and development environment.
So the single node obviously is a really basic architecture. In many cases, it's just a case of spinning up a node or putting a machine in a rack, installing the operating system, and then just installing Postgres and using it. That's great for dev and test. It's great for non-critical business applications, ones where you're not overly concerned if it's down for a day, if something goes wrong and you have to restore from backup or anything like that. But in any serious production environment, you're going to need a multi-node setup. So we're going to present two today, one with asynchronous replication, which is the easiest and the most performant option. And we'll also look at them in a minute at synchronous. So in a multi-node cluster with asynchronous replication, we'll have a primary server with one or more typically hot standby servers. So when we say hot, what we actually mean is that you can run queries on them. So they're only read-only queries. So you can't, we're not talking about multi-master replication or anything like that here. But you can use them for things like offloading report workload, or even load balancing. If you've got a way of splitting your read and read write queries, then you can offload that to the standby servers. Now, one thing to remember though is that this type of cluster is replicating asynchronously. So there's a couple of things to bear in mind there. If you're load balancing across them, you may find that your application will execute a write query, but that's not necessarily instantly visible on the standby servers. So you need to make sure that your application is prepared to deal with that. And the other thing to bear in mind is that if you have a failure of the primary server and you need to fail over to one of the standbys to take on the read-write workload, it's possible that transactions may be lost during failover, the ones that haven't yet been successfully replicated across. Now, Postgres is very careful about how it does this. You will only lose completed transactions. So you won't end up in a state where half of a transaction has been replicated, but not the other half, thus leaving you in a state where you've got inconsistent data. But again, that's something that you need to be aware of and design your system accordingly. The replication lag may cause you to lose one or more transactions during a failover event. Now, we say here the recovery time objective is typically less than 60 seconds. That's because you can fail over very quickly. Obviously, that requires tuning and appropriate monitoring, and we'll look at how that's done in a moment. The recovery point objective, as we say, typically will just up to a few seconds. It is dependent on what the replication lag on the system is like. That replication lag on some systems will be almost 0 or even 0. On others, it may be a second or two. It just depends how busy your system is, what the workload's like, and how well your servers are keeping up with that workload. The geographic redundancy is dependent on node placement. If you're running a cloud environment, then you might use multi-availability zones. So, for example, on Amazon, that might mean using US East 1A and 1B and 1C. So everything's in the US East 1 region, but with different servers in the cluster in each of those availability zones. Target availability, we'll say 99.99%, assuming that nothing else fails in terms of hardware or environment or network and so on. But it is theoretically possible to get up to 5 nines with appropriate tuning of failover. Now, if we actually look at what that architecture looks like, we'll see an example here where we've got 3 servers. So the top server is the primary database server, and you can see the read-write connections from the clients indicated by the green lines going only to the primary database server, and then read-only connections with the red lines coming from the standbys as well. Each of those individual nodes may well be set up exactly the same way as you might set up a single node, i.e. it's a database server and optional volumes for things like write-ahead log and for the data. Then on the right-hand side, you'll see the asynchronous replication between all of the nodes in the cluster, starting from the primary and being pushed out to the 2 standby servers. And from a geographic point of view, as I noted earlier, you've got multiple availability zones. So each one of those nodes is in a separate orange box indicating the availability zone that it's in. So, moving on to synchronous replication. So again, we have a primary server with 1 or more hot standbys that we can run read queries on. The difference here is that we're using synchronous replication. And what that means is that when you run a write query on the primary server, it won't report that the transaction is completed to the client until such time as at least one of the, or in a typical configuration, at least one of the standby nodes has reported back to the primary that that transaction has also been written there. The idea being that you're guaranteed that all transactions are on at least 2 of those nodes before the client is told that the transaction has been completed and committed as it should be. Now, as you can imagine, because there's all the extra handshaking involved here of the standby server needing to report back to the primary that it's written the transaction to non-volatile storage, the synchronous replication option is less write performant than asynchronous. But it does mean that you don't get any loss of committed transactions if a failover happens, because multiple nodes have got the committed transactions on them. Now, of course, it is still possible to get transaction loss in the event that you lose 2 nodes at once. But by designing your cluster appropriately, using different geographic options and so on, that risk can be minimized to near 0. RTO, GPO, RTO, RPO, GRO, and target availability are all largely the same as they are for the asynchronous cluster. The only real difference being that you've got no loss of committed transactions. Moving on to have a look at what that looks like, you'll see the diagram is actually almost identical to the one for asynchronous. The only real difference is that you'll see that we've noted on the right-hand side where the replication is shown as in the light blue lines, that we have synchronous replication across to the first of the standby servers. And the second one is still running with async replication. And you may ask why typically we wouldn't have every node running with synchronous replication. And the reason is simply performance. If you've got 3 nodes or 4 or 5 nodes, then having to have every single one of those acknowledge that they've written the transactions to non-volatile storage before the client is told that the transaction is committed, obviously adds to the overhead and will slow things down significantly. So those are the core architectures. We'll have a look now at some of the different add-on architectures. So these are options that you can employ on top of one of the core architectures. Some of them you can use together, some of them you wouldn't. So first of all, we're going to look at pooling and load balancing options. We're going to present 2 different options here. You would typically only choose one or the other of these if you need to. Vibor.
Yes. So load balancing is a kind of add-on to the core architecture, right? Because load balancer like PG Bouncer gives a lot of advantage from the scaling perspective, also from minimizing the connections to the Postgres. It also reduces the connection start time. So when application is requesting a connection is already created. So and it's just only redirecting the request to the open connections. PG Bouncer and a lot of people actually uses the connection or load balancer to load balance their read queries across the different database node. I think as Dave mentioned in the previous core architecture, if you have a multi-node architecture, maybe asynchronous or synchronous, and you want to load balance your read queries on the standbys which you have, you can use load balancer like PG Bouncer, where you can have 2 bouncers running, one for read write, one for read only purpose. And this way you can equally divide the load across the nodes which you have in your reference architecture. So this is the, you can see there are the 2 different architecture presented here. In one, you can see there's only one PG Bouncer node. All clients are connecting through this PG Bouncer node to the different database server nodes. And PG Bouncer knows where to redirect the connection based on the database request coming from the client. Other way you can look at it, this add-on functionality of the PG Bouncer, you can run the PG Bouncer on each Postgres database node. And this way you can have more PG Bouncers, and client can actually connect to any one of the database node, and PG Bouncer would be able to redirect those requests to a specific database based on the load on the system. So it's a very interesting architecture. Here we are just showing you the 2 different architecture, but if you want to have more PG Bouncer node, you can have that in a separate environment. There is also what people do using this as a foundation for building their own environment based on the SLAs. What people do, they actually put the PG Bouncer, for example, if they're deploying in the AWS cloud, they put the PG Bouncer into the auto scale environment where they can spin up more and more PG Bouncer nodes, and then after that, PG Bouncer can automatically rewrite the connections to the specific database node. And when they are done with the load on the system, they can reduce, because auto scaling allows you to scale more and more node, add more and more node. And when they're done, they can actually drop down the number of nodes which they have in the environment. So as we mentioned, that this is purely a foundation. You can do a lot more on this foundation. The other load balancing tool which people use it are add-on, I would say, item which they add into the foundation or to the core reference architecture is PG Pool. PG Pool gives some more advantage on the PG Bouncer. Again, it's also connection pooler. So whatever advantage which you can see with the PG bouncer, you will get with the PG pool. These additional advantage which is available in the PG pool, that is, it actually allows you to redirect the read query or load balance the read query on the hot standbys or across the nodes which can allow the read queries, right? But when you're using it in the production, you need to make sure that there are um, certain things which you need to take care when you are using in your production environment or when you're using with the application. PG Bouncer has the mechanism to find out whether the query is a read-only query or read-write query. But in certain scenarios, like for example, if you are trying to perform a select on a views, or when you are using a function calls, right? PG pool may not be able to detect whether it's a read-only query or read-write, because under the hood of the function definition, you may be performing some write-up activity. Or maybe if you have updatable views, it may be performing a some write activity on the node. So in that case, load balancing can be trickier. So again, there are some mechanism available in the PG pool to handle those situations. And that's why you would like to tune your PG pool deployment. Um, PG pool also comes with its own high availability. You can use that PG pool for that purpose. Next slide, please.
Sorry, I hit the wrong button.
It's okay. So there are some more add-on items which you can add to the architecture, reference architecture. This is mainly from covering some or adding some more capabilities and the features to the core architecture which we have discussed. Like for example, if you want to give the visibility to all the components which you have in the reference architecture, or if you want to monitor, or if you want to manage the tools or the items which you have included into your reference architecture, you would like to deploy a software which can help you to achieve that. And that's why there is a Postgres Enterprise Manager, which you can use, which can give you the visibility across the node, gives you visibility on the high availability, also gives the information about how you can monitor and manage the things. But that there is a one tool which can help you to achieve your RTO requirement, recovery time objective, or recovery point objective. That's called backup and recovery tool BART. And we will be covering more detail about these two tools in following slides.
Yeah, thank you, Vibhor. So Postgres Enterprise Manager is a 24/7 monitoring and management application that we provide for use with either PostgreSQL or EDB Postgres Advanced Server. If you've used PGAdmin, you'll be familiar with much of the core user interface of PEM, which is based on PGAdmin and provides all of the underlying PGAdmin functionality. In addition to what you find in PGAdmin, PEM also gives you 24/7 monitoring and alerting. There are, I think, a couple of hundred of what we call probes out of the box, and a probe will monitor one or more metrics from a different aspect of your system. That might be a particular table or function, or it might be an entire database and database level statistics. It might be the database server and the statistics related to that, or it might be the operating system and the hardware. So PEM will automatically monitor many aspects out of the box, and then you can, in addition, configure the monitoring that you need for application-specific things such as individual tables and functions and so on. The monitoring then feeds nicely into an alerting system. So you can set up PEM so that it will give you alerts via email when certain thresholds are crossed. So for example, if your number of users exceeds a certain predefined limit, or if your disk space starts to run out. And you, as I say, you can receive those alerts via email, via SNMP traps if you're using an upstream network monitoring system. We can also integrate directly into Nagios if you're using that. And I know the development team at the moment are working on a prototype for webhooks to allow you to integrate into anything that allows REST API calls to be made. So hopefully in a not too distant version of PEM, you'll be able to even send alerts directly to things like Slack. We also have a number of pre-built dashboards with lots of useful graphs and information that you'll want to look at while you're monitoring your production systems. Predictive reporting, so you can run reports that will predict when you're going to run out of disk space, for example. Modern versions of Postgres have wait states, and if you're using EDB Postgres Advanced Server, we have a wait state collection system that's kind of like active session history if you're familiar with Oracle. So it will collect and periodically, I think it's every 5 seconds by default, sample what weights are in the system at any particular time. And then PEM allows you to analyze that data in depth and drill down onto performance issues. So you can very quickly figure out, am I CPU bound? Am I IO bound? Are my queries creating lots of locks, which are slowing things down, that sort of thing. There's a SQL profiler in there, which is also a very handy tool. So that allows you to record all the workload that's happening on a server for a period of time and then analyze that later on. That's a very handy tool, because one of the things that it does is give you aggregate statistics. So for example, you might have some fairly heavyweight queries that just run periodically and don't actually cause issues on the server. But then at the same time, you might have running lots of lightweight queries, but those lightweight queries happen so often that in aggregate, they're causing you performance issues. And the SQL profiler helps you identify those by telling you this, during the period you were monitoring, this particular query ran 87,000 times. And whilst each individual instance of that query was very lightweight in terms of load, in aggregate, that query is responsible for 90% of the load on the system. And that can also be very, very helpful when you're trying to debug what's going wrong when you have performance issues. There are various other tools in there as well. If you're interested, I'd suggest you take a look at the website and download a copy and try it out. In terms of the actual architecture for deploying this, basically you run typically a dedicated PEM server, so that will be on an additional node, and then that will communicate with each of the database servers that you're monitoring. We have concept of what we call a fully managed server. So these are the top two on the right-hand side here. So each of those will be running an agent that is reporting metrics back to the PEM server on a continual basis. And it's also running periodic tasks that the PEM server might tell it to do, like reconfigure the database or do a database restart or import the logs from the log directory and so on. If you're running on a system where you can't run an agent, then you can run in what we call remote monitor mode. In that case, the PEM server itself will be monitoring statistics from the database server, but it does introduce some limitations. So for example, you can't restart the database server remotely or make certain types of configuration changes. And there are some aspects of the underlying operating system and hardware that can't be monitored in that fashion. PEM itself, like pgadmin, is a web application primarily, so clients will connect to the PEM server, typically over HTTPS, and interact through Chrome or Safari or Firefox or whatever the preferred browser is. And this can be added on to any of the reference architectures that we've discussed so far. you can install the PEM agent on any of the nodes in the cluster and monitor them as you need to. So as Vibor mentioned, another almost, well, for most people, it is a critical part of the infrastructure is backup and recovery. We typically use our BART tool for that. So one thing to keep in mind is having a cluster of database servers gives you lots of different copies. And if you're doing point-in-time recovery, shipping, keeping copies of the write-ahead log, then that does give you the option of restoring the database to a point in time in the past. However, that's not a substitute for backups. Even if you have multiple nodes in a cluster, if somebody drops a table on the primary, that drop is going to cascade across to the standbys pretty quickly, usually within less than a second or two. So it's pretty important that not only do you have multiple copies of the cluster so that you can fail over when you need to, but that you also do take regular backups. So if you need to restore the whole thing, you can do that. BART gives you these capabilities, makes it much more easy to manage those backups. You can do full backups with it. You can do point-in-time backups. It can manage the well as it needs to do that. And it can also do block-level incremental backups, which can be very useful for saving space. Perhaps more importantly for many people as well, we can manage BART directly through PEM. So you can do everything graphically. You can have multiple BART servers running and PEM scheduling backup jobs on all of those and allowing you to do, I'll call it a one-click restore, but it's not quite one click because obviously we need to confirm that you really do want to restore a database before proceeding for obvious safety reasons. So the architecture for that, again, this applies to any nodes within the cluster that you want to back up. We would typically have a dedicated BART server, and that will have access to all of the different database servers. It will connect via a combination of libpq, which is the Postgres wire protocol, and over SSH so that it can get copies of the write-ahead log files that are needed to do point-in-time recovery. And we'll also use that SSH connection for doing restores if it needs to reinitialize the database and so on. BART itself will need some kind of storage on which to store your backups. Now that could be direct attached storage in the BART server itself. It could be as depicted on the diagram here. It could be fiber channel to a SAN, and then the SAN in turn maybe is being backed up to a tape library, something like that. That's really up to you how you choose to configure it, but hopefully the intention of these architectures is to give you a starting point for your own designs, and an easy way, as Vibor mentioned earlier, to try things out and figure what's going to be right for your organization and will meet the needs of your disaster recovery policies. So that's it for the architectures that we wanted to present today. They're available on our GitHub. As Molly mentioned, we'll be sharing more details afterwards. But if you go to GitHub/EnterpriseDB, you'll find the reference architectures repository there. There are more details than we've shown on the slides here. As I mentioned, we will be expanding those over time to include more detail and more different options about how you can actually deploy some of these in different types of environments, such as AWS and Kubernetes, and adding capabilities. So for example, we'll be looking at things like logical replication and different poolers and other tools that people might want to use. Vibor.
That's true. And I think, as you can see, everything is a kind of an add-on to the core architecture. The core architecture is a key thing. The foundation, which we have shown you about the multi-node or single node, right? The foundation for the multi-node, for example. We have given example for the 2-node or 3-node cluster, right? You can have as many as standbys you want. As I mentioned that this foundation can be actually extrapolate to any kind of a scalability. Like a lot of customers, what they do, they create a mechanism for adding more and more standby for read purpose or for their own reporting purpose in the auto scale mode, and they reduce those number of standbys based on as the load get decreases over the period, right? Or if they are done with their work. So and the same for the other add-on items which you have seen in the for reference architecture like PG pool and PG bouncer. You can auto scale those, and again you can bring it down based on the load on the system. So it's a foundation, and you can do a lot more. We have one more webinar session coming up on the automating a Postgres high availability architecture with Ansible. In this, what we want to show you, how you can easily deploy these reference architectures or the core architectures and the add-ons using a one single command. How people are really using this reference architecture in their production environment, how they are actually automating the whole environment so that for their critical application and for the non-critical application, they can choose which reference architecture they would like to use based on the use cases. Like, for example, if somebody is developing an application, or they are in the development phase, or they're testing the application against the database, they sometimes use single node architecture. If they are going and if they want to deploy a mission critical applications in the production, they go with the multi-node reference architecture, and how they automate the whole thing using the Ansible and other DevOps tools. A lot of these things will be coming up into our next webinar session, which is on November 11th. We will be covering some important DevOps tool with the survey, which we did with our customers and what we found.
Thank you, Vibor. So that concludes the slides that we wanted to run through with you today. Molly, I think we have some time for some questions.
Yes, we had some great questions today. So we'll jump right in. The first question that I'm going to ask you is, someone asked, can PEM send text message alerts?
PEM cannot send text message alerts directly itself. However, one of the options when alerts occur that I didn't mention is that it can actually execute an arbitrary script. And you can have that script be executed either on the server that the alert originated from or the PEM server.
Yeah.
So if you have other tools and other software that allows you to send SMS text messages from the command line, then certainly you could use a custom script very easily to send those alerts through that tool to your mobile phone.
Right, and one example I would like to give you, a real-time example. What people have done, they use PagerDuty for sending the text or messages, right? And PAM can be easily integrate. I mean, they can easily integrate PAM with the PagerDuty, for example. In the same way, if you have any other tool which you might be using in your environment for texting, sending notifications, right? You can easily integrate PAM alerting capability with those third-party tools.
Yeah, and those you can use those tools, you can use PEM to call Python scripts, for example, or to call curl or wget on the command line if you want to actually call a REST API of something else.
Mm-hmm.
So that does give you a way of doing things like integrating with Slack right now, for example. But as I mentioned, I know we are looking at a not too distant future version of PEM having native webhook integration as well, which will make that even easier for those particular type of use cases.
Okay, great. Another question that we had was, why do I need to use external tools for connection pooling?
That's actually a really good question, and it's not necessarily an obvious answer. First of all, the obvious part of the answer is that Postgres doesn't have connection pooling built in. And traditionally, Postgres has been built around the theory of allowing it to be a building block. So, you know, we have lots of hook points, lots of built-in APIs, and we try and make sure that Postgres doesn't try and do everything itself, because then we have a fairly rich ecosystem of plugins and extensions and other tools that you can use with Postgres that allow you to select what is the most appropriate for your environment. Now, why we actually need connection pooling, starting up a new connection to Postgres is relatively expensive. You know, all the initialization, the creation of the new processes and things like that that go on when Postgres starts a new connection, it's not the cheapest thing in the world. So typically what we'll do is on very high load systems, we'll use a connection pooler so that we can have all those connections all started up and ready to be used, and then shared amongst what may be a much higher number of client connections that come into PG Bouncer or PG Pool. Now, the other reason why we might use connection pooling is not just for connection startup performance, but performance in general. Every time a new connection starts in Postgres, there are various data structures that are set up to support the number of connections that you have in total. Now, as those data structures internally will become bigger when you configure Postgres for more connections, you can potentially run into performance issues because it's got to coordinate all of those different connections that it's configured for at any one time. So using a connection pooler allows us to share connections between multiple clients, and thus allows the backend database server to run much more efficiently. And when you think about the way most clients work, it's very rare that you have an application that is hammering the database constantly. Most applications will run a query, then wait for the user to do something, and then run another query. So it's much more efficient if we can share a limited number of connections between multiple clients than if we configure the database to accept the number of connections that we might have at peak times.
Right. The other part is there's one more item which you can think about. Let's say if you have exhausted the connection to the database side, then it could be possible database your application will start receiving the error messages when it's going to make additional connection to the database. But if you use a connection pooler like PG Bouncer, these connection poolers can actually queue your request before erroring out to the applications, which may sometimes break the application or sometimes create some weird behavior at the application side. So to avoid that kind of a situation, you can use PG Bouncer or any other connection poolers.
Okay. All right. Another question that we got was, is it possible to load balance read/writes PG Bouncer in a clustered environment?
So PG Bouncer, unlike PG Pool, PG Bouncer doesn't inspect what queries are going through the connections that are coming into it. So it has no way itself of being able to distinguish a read query from a read-write query. However, what a lot of people do when they design their applications, they'll actually separate out read and read-write connections in the application. So they may have two different connection strings, for example. And all the read-write queries go to one and all the read-only queries go to another. PG Bouncer allows you to set up multiple connections. So it can have one connection which just goes to the primary. And then it can have another connection that will use a round robin approach, usually based on DNS or similar techniques, to communicate with all of the servers, or maybe just all of the standby servers. So it can route all the read connections through to all the standbys, and then separately route all the read-write ones to the primary. The main advantage of PG Pool over it is that PG Pool will inspect the queries that are coming across the wire. So it can do that automatically. So you don't need to have multiple connections from your application. But there are two downsides to that. One is obviously inspecting the queries as they come across the wire and imposes a performance impact, which you need to be aware of and need to test for that before going into production. The second, as Vibor pointed out when he was on the slides about PG Pool, is that whether or not a query is read-only or read-write is not always obvious from the actual SQL query, because write actions might be masked by calls to stored procedures, for example. So even you might have what looks like a select query, but actually there's a trigger and a function that is going to write an audit record into a table to say that you've made that query. And PG Pool won't necessarily be able to figure that out from what it sees on the wire. So PG Pool can be very powerful, but you need to be careful how you use it and be aware of the things that might trip it up, and make sure that your application doesn't do any of those things, or where possible, configure PG Pool to recognize certain queries that might be read-write, but are not obviously read-write if you just look at the SQL syntax used.
Right. So yeah, you would like to test your application against the PG Pool before you make a decision. Play all the scenarios when you are planning to use PG Pool on the core reference architecture.
Okay, great. So we have time for just one more question. This is one of the first questions that came in today. It was, can I have a 4-node PostgreSQL cluster?
Yes.
Yes.
Very simply, you can have as many nodes as you want, and you can even have cascading replication if you're using the streaming replication functionality, where one standby will cascade to another standby and so on. Theoretically, you can have as many as you want, pretty much, especially once you start using cascading. In practice, you probably don't want that many, because it just becomes a pain to manage for usually no benefit. The one thing I will note is, if you're using synchronous replication, make sure you always have at least 3 servers in the cluster. Because if you have a failure of one server when you're running synchronous replication, then if you're on a 2-node cluster, then as soon as that one of those servers fails, you're only on one server, right? Which kind of makes the point of having synchronous replication, to make sure that everything is on at least 2 servers when it's committed. It invalidates that point. So if you're using synchronous replication, always plan to have at least 3 servers in the cluster, so that even if one fails, you've still got your data on at least 2.
All righty, okay. Anything else that you'd like to add, Vibor? Are you all set?
I think all the points are already covered by Dave. So yeah, always ensure that in synchronous application, you at least have 3-node cluster. And if you want to add more, you can add more. The other thing which I would recommend that when people are using synchronous replication, they should thoroughly test the performance, because when you use synchronous replication to ensure that you don't lose any data, Postgres also makes sure that data is really copied over the wire, over the network to the standby, right? And it only confirm the data is written to the application after it gets the confirmation from the synchronous standby. So make sure you test it well, and ensure that if you are going with the synchronous application, latency between the nodes should be low, right? So that you can get a better performance.
All right. Well, thank you so much both for speaking today. Apologies for those questions that we were unable to get to live. They will be answered and you will be contacted after the webinar. Thank you all for joining us today. We will be sharing the recording along with the slides with you as soon as possible. And I hope you have a great rest of your day.